Hello AP Chemers, we're going to talk about solubility equilibria today. So specifically we're talking about ionic substances that are slightly soluble. We call them slightly soluble or insoluble or sparingly soluble because very, very little of the solid actually dissociates into its ions and dissolves. So things like silver chloride or silver bromide or lead chloride or something like that, those are very, very slightly soluble. If I wanted to write the K expression for these, just like I would for any type of reaction, so the KSP is going to be the concentration of the Ag plus ion times the concentration of the Br minus ion. Now, this is just our K, but we give it a special name. We call it KSP. That stands for solubility product constant because we're dissolving, so solubility product is always a product, and then constant since it's the equilibrium constant. Let's try the FeOH2. So the KSP for that one, expression would be the concentration of the Fe2 plus times the concentration of the OH minus squared. All right, let's try another one. So it tells us that the solubility of AgI is 1.22 times 10 to the 8th moles per liter at 25 Celsius, and it wants us to calculate the KSP. There we go. So if you look at this number, this is really, really small. It's 0.0000122 moles per liter. So that's how many moles of the AgI can dissolve in a liter. That's really, really tiny. So that tells you it's very sparingly soluble. Anyway, so if you are trying to calculate the KSP or K or an equilibrium constant, what you want to do is write your equation first and then write your K expression. So let's do that. So AgI solid dissociates partially into Ag plus and I minus. Let's write our KSP expression. Concentration of Ag plus times the concentration of I minus. Now, we need to plug in numbers in there. They don't give us the concentrations of either the Ag plus or the I minus. However, the only source of the Ag plus and the I minus is the AgI solid, and it's telling us that the AgI dissolves to that extent. So that's the molarity of the AgI as a saturated solution. If I had a saturated solution, this would be the concentration of the aqueous AgI. And so since this is a 1:1:1 ratio, then that means that this is also the concentration of the Ag plus, and it's also the concentration of the I minus. So I can just plug those in. So KSP is going to be 1.22 times 10 to the negative 8th molar. That's the concentration of my Ag plus, times 1.22 times 10 to the negative 8th molar. That's the concentration of my iodide. Multiply those together, and we end up with 1.49 times 10 to the negative 16th. That is a really, really small number. Remember, K tells us, if you have a really high K, that means that the reaction or the process is very product favored. If it's really small, then that means it's very reactant favored. So if you look at this number, that's an extremely, extremely small number, and so that tells us that most of the AgI stays as solid. Very little of it turns into ions, or dissociates, I should say, into ions with the water in between it to dissolve. So that makes sense because my saturated solution is very, very low in concentration. Let's try another one. So we want to calculate the KSP for PbCl2 if the solubility of it is 1.62 times 10 to the negative second moles per liter. So, this looks like it's much more concentrated as a saturated solution than the AgI there, so I would expect my KSP to be a little bit higher. So, same thing as before, we want to write our equation. So PbCl2 solid, that dissociates partially into Pb2 plus, and then 2Cl minus. We'll write our KSP expression. Concentration of the Pb2 plus ion times the concentration of the Cl minus ion, and then don't forget to square it. Now, they don't give us the concentrations of either one again, but they tell us that the concentration of the PbCl2 itself, if it was a saturated solution, it's going to be 1.62 times 10 to the second molar, negative second molar. And my only sources here of the Pb2 plus and the Cl minus are from the PbCl2, and it's a 1 to 1 to 2 ratio, and so if this is the concentration of my PbCl2, then it's also going to be the concentration of my Pb2 plus. It's a 1 to 1 ratio. So I can plug that in there. 1.62 times 10 to the negative second molar. That's my Pb2 plus. My Cl minus also only comes, the only source of it is from the PbCl2. And if the concentration of the PbCl2 is this number, the Cl minus is double that number because it's a 2 to 1. There's 2 chloride ions in every one of these. And so my concentration for the Cl minus in that case, since they don't give it to me and I need to find it through the PbCl2, is just double what the PbCl2 would be. Now, don't forget that the expression itself has a squared, and so we're going to square that concentration. So this by itself is the concentration of my Cl minus. The squared comes from the expression. So you multiply those together and you get 1.7 times 10 to the negative fifth, which, is a small number. It's still reactant favored. However, it's much, much bigger than this number is. And so PbCl2 is more soluble than AgI, which makes sense looking at the concentration of a saturated solution here. This was 10 to the negative second moles per liter. The other one was 10 to the negative eighth moles per liter. Let's try one more. Determine the solubility of the salt CaCO3 in both moles per liter and grams per liter if its KSP is given to you. So, since talking about KSP, you start it as always, you write out your dissociation equation and the K expression. So let's do that. CaCO3 solid dissociates into Ca2 plus CO3 2 minus. We're going to write our KSP expression. It is the concentration of the Ca2 plus times the concentration of the CO3 2 minus. Now in this case, they give us what the KSP is. They give us that it's 3.8 times 10 to the negative ninth. What do they want? They want the solubility. Solubility means how much can dissolve. In other words, they want the concentration. What do they want the concentration of? They're looking for the concentration of CaCO3 as a saturated solution. So if I make a saturated solution, what concentration of CaCO3 would that be? And that's kind of a valuable question because sometimes, like when we're prepping labs, the directions tell us make a saturated solution of this. Well, how do I do that? One of two ways. You could either just keep adding and dissolving until no longer it can dissolve, or the other way is to, if you look up your KSP, you can figure out what concentration that should be, and that's a lot easier or less time consuming. So I don't know what that is. I don't have any other numbers except for the KSP, so I'm going to say, well, let that be X. If the concentration of the calcium carbonate as a saturated solution is X, what would be the concentration of the Ca2 plus ion? Well, it's also going to be X. And the concentration of the CO3 2 minus is also going to be X because there's only one source for the Ca2 plus and the carbonate ions, and they're all 1 to 1 to 1 ratio with the calcium carbonate, and so all of them would be equal to X. So then what I could do is I can plug in this for the Ca2 plus and this for the CO3 minus. So I'm going to do that. So this is going to be X times X, and that way I can solve for what X is. X turns out to be, in this case, 6.16 times 10 to the negative fifth molar. And that is my concentration of the CaCO3. It also wanted it in grams per liter. They asked for moles per liter and grams per liter. We can easily change that, so that's one of our answers. For grams per liter, all we have to do is convert that, so 6.16 times 10 to the negative fifth molar means moles per liter. I want it to say grams per liter, so I'm going to put moles on the bottom so they cancel grams on top, so it would say grams per liter. And to link between the moles and the grams, I just used my molar mass. It's about 100 or 100.1. Oops. So that ends up being 0.00617 or 6.17 times 10 to the negative third grams per liter. And that's my answer. Let's look at the next one. We want to determine the solubility of MgF2 in grams per liter, and they give us its KSP value. So it's very similar to the one that we just did with the calcium carbonate, except the ratios now are not 1 to 1 to 1. So first we're going to write out our dissociation equation, so I'll write that on top here. MgF2 solid dissociates into Mg2 plus and 2F minus, and I'll write my KSP expression. It is the concentration of the Mg2 plus times the concentration of the F minus squared. What are they asking for? They are asking for the solubility of the MgF2. That means I want the concentration of the MgF2, the aqueous MgF2, if it was a saturated solution. So if I keep dissolving until no longer anything can dissolve, what would be the concentration of that? So since I don't know what it is, I'm going to let it equal to X. If that was equal to X, then what is the concentration of my Mg2 plus? Well, it's also going to be X because it's a 1 to 1 ratio. What would the concentration of my F minus be? Well, it's going to be 2X because it's a 1 to 2 ratio. There are two fluoride ions in one MgF2. So what I could do then is I could plug in X for the concentration of the Mg2 plus and 2X for the F minus. So I'll go ahead and do that. So this is X, and then this is 2X, and then don't forget that that is squared as well. My KSP is given to me as 6.4 times 10 to the negative 9th. So that, remember that this is, the concentration of the F minus itself is 2X, and so that whole thing is squared, which means that's 4X squared, and then times this X, so 4X cubed. So I take this number divided by 4 and then cube root it to get my X. My X ends up being 0.00117 molar. And that is the concentration of my MgF2. However, they wanted it not in moles per liter, but in grams per liter, so that's pretty easy to do. 0.00117, molar means moles per liter. So I'll put moles on the bottom so it cancels, grams on top. Molar mass is 62.3 grams per mole. And so this gives me 0.0729 And actually, I should probably start doing sig figs. It's 0.073 grams per liter. The next question asks which is more soluble, and it gives you a pair of salts. So let's start with AgCl and AgCN. So first we're going to write our dissociation equations. So here are the dissociation equations and the KSP expressions and also the KSP values. So if you wanted to figure out what the concentration of the AgCl is in a saturated solution, you would say, well, it's equal to X, which is equal to the Ag plus concentration, which is equal to the Cl minus concentration. So that's going to be equal to X times X. And if you wanted to know what X is, you would just take the square root. And same thing for the AgCN as well. So if your salts are all the same ratio, molar ratios to the ions, like this is a 1 to 1 to 1, 1 to 1 to 1, they match, all you have to do is just check the value of the KSP. Whichever has a higher KSP is more soluble. Whichever has a lower KSP is less soluble. So in this case, the one that is more soluble would be the AgCl because it has a higher KSP, meaning that there are more ions or more products compared to this one. Okay, obviously both of them are reactant favored, but this one is less reactant favored than that one. So if you look at the next one, where we have MgOH2 and CaOH2, they also have the same ratio. So you can just compare the KSPs right away. But just to show you that, I'm going to write out the equations to show you that they are the same ratios. So here are the dissociation equations and the KSP expressions for both of them. They're both 1 to 1 to 2, 1 to 1 to 2. So if you wanted to figure out what the concentration of the magnesium hydroxide or the calcium hydroxide is in a saturated solution, you would set that equal to X, and then you would say, well, the magnesium concentration would also be X because it's a 1 to 1. The hydroxide concentration would be 2X because it's a 2 to 1, and then don't forget your squared there, so 4X cubed is equal to your KSP. And so to find X, you would take, you divide by 4 and then take the cube root of that. Same thing with this one. You would say this is X and then this is 2X, but then don't forget your squared. So again, 4X cubed, and if you wanted to find X, you would divide by 4 and take the cube root of it. So since they are the same ratio without even plugging into your calculator, you can say the one with the higher KSP, which would be this one, the bigger KSP means that you'd have more ions associated and therefore more soluble. And so this has a higher KSP, and so it is more soluble. Again, you don't even have to write all that as long as they're the same ratio. Now the next one, they do not have the same ratio, so it is not okay to just look at your KSP. So I'm going to go ahead and write my dissociation equations first. And I'll write the KSP expression, and we'll look at which one is going to be more soluble. So I'll start with the FeCO3. That dissociates into Fe2 plus and CO3 2 minus. My KSP expression is going to be the concentration of the Fe2 plus times the concentration of the CO3 2 minus. The next one is Ag2S. That dissociates into 2Ag plus S2 minus. My KSP expression is going to be the concentration of the Ag plus squared times the concentration of the S2 minus. So, if you wanted to find what the concentration of the FeCO3 or the Ag2S would be in a saturated solution, you would say, well, let's set that equal to X, and you'd look up your KSP. My KSP for the FeCO3 was 2.1 times 10 to the negative 11th, and you'd say, well, if the FeCO3 concentration is X, then this is also X, and this is also X, which is x squared. So my x, which is the concentration of the FeCO3 as a saturated solution, would be 4.6 times 10 to the negative 6 molar. Okay, let's look at the next one. Ag2S dissociating into Ag2Ag plus and S2 minus. Here's my KSP expression. My KSP that I looked up was 1.0 times 10 to the negative 14. Now, if the concentration of the Ag2S as a saturated solution is X, my concentration of the Ag plus would actually be 2x, because there's 2 silver ions for every 1 Ag2S. And then don't forget that's squared. And then the S2 minus would be x, because it's a 1-to-1 ratio with the Ag2S. So that is 4x cubed. And so if you solve for x, which would be the concentration of the Ag2S as saturated solution, that ends up being 1.7 times 10 to the negative 5th molar. That's a 5 there. So here's this one. So that's what you compare. And you can see that I can dissolve a little bit more of the Ag2S than I could of the FeCO3, even though this KSP is smaller than this KSP. So you can only compare the KSP directly if they're all the same ratio. But since this is a 1-to-1-to-1 and this is a 1-to-2-to-1, those are not the same ratio, so you actually have to do the math and figure out what x is. So in this case, it looks like my Ag2S is slightly more soluble.